Unit 8, Chemical Bonding, pages 181 to 186, focusing on formal charge. Formal charge is an electron bookkeeping method. It's used to check if the arrangement of electrons around a particular atom in a Lewis structure makes sense. Formal charge does not give the actual charge on the atom. Each atom in a Lewis structure has a formal charge that is calculated from this formula. For any specific atom in a Lewis structure, the formal charge is equal to the number of valence electrons minus the number of non-bonding electrons minus 1 electron for each bond pair of that atom. So formal charges of OF2. An isolated oxygen atom has 6 valence electrons. So we will say 6 minus, and then we'll count around the oxygen. 1, 2, 3, 4, 5, 6. 6 minus 6 means this oxygen has a formal charge of 0. Notice I counted each dot, 1, 2, counted the dash as 1, so that's 3, 4, 5, and then 6. For my fluorine atom, it has a valence of 7 minus 1, 2, 3, 4, 5, 6, 7. 7 minus 7 gives each of these fluorine atoms a formal charge of 0 as well. And so we can put a 0 there because these are the same math. In this OF2 molecule, there are 4 non-bonding electrons on the oxygen atom and 2 bonds on the oxygen atom. The formal charge of oxygen is going to be 6 minus 4 minus 2 is equal to 0. An isolated fluorine atom has 7 valence electrons. In this OF2 molecule, there are 6 non-bonding electrons in the fluorine and 1 bond. The formal charge for fluorine is 7 minus 6 lone pairs minus 1 bond equals 0. The sum of the formal charges on all atoms in the molecule must be equal to the charge on the molecule. This can be used as a check that the formal charges were calculated correctly. So here's another example of calculating formal charge. A student wrote this improper Lewis structure for OCS. The figure shows the formal charge calculations. That this has a formal charge of 0, 6 valence minus 1, 2, 3, 4, 5, 6 equals 0. The carbon has 4 valence minus 1, 2, 3. 4 minus 3 equals a plus 1 formal charge on this carbon. And then the sulfur has 6 valence minus 1, 2, 3, 4, 5, 6, 7. 6 minus 7 equals a negative 1. So we have a 0, plus 1, and minus 1 charge here. The sum of the formal charges must be the charge on the molecule. So 0 plus 1 and minus 1 gives you a 0 overall, and the charge on the molecule, in fact, is 0. Using formal charges to choose Lewis structures. Sometimes more than one possible Lewis structure can be drawn. Formal charges are used to decide which structure is more likely to be the best Lewis structure. Lower formal charges are better than higher formal charges. Ideally, all atoms should have a 0 formal charge. Negative, and this is ideally, it doesn't mean they do, it's just ideally it would be best if they all have a 0 formal charge, but they might not. Negative formal charges should be on the more electronegative atoms. This is a very important statement right here. In other words, a structure with a positive formal charge on the most electronegative atom would be unlikely. Example of using formal charges to decide the structure. Here are 2 perfectly valid Lewis structures for CO2. Every atom has an octet. Both structures could have resulted by following the rules given above, which is more correct. So here we have a formal charge of 0 on this oxygen, formal charge of 0 on the carbon, and a 0 on this oxygen. So everything is 0, and each atom has a 0 formal charge. Here you have a negative 1 on the oxygen, a 0 on the carbon, and a plus 1 on this oxygen. So overall, we do have a total of a 0 formal charge. However, it's not ideal because there are charges that are not 0 present. So we need a 0 overall for both of them. However, the one that has the most atoms with a 0 formal charge is the more ideal Lewis structure. Structure A has ideal formal charges of 0 on each atom. Structure B has 2 problems. The formal charges are higher than structure A. The oxygen with a triple bond has a plus 1 formal charge, so the atom with the highest electronegativity has a plus 1 formal charge. This is not a good situation. Understanding the meaning of formal charges. Atoms combine together to make molecules. Each atom shares electrons to make covalent bonds. The number of bonds made by a particular atom is determined by how many electrons the atom requires to reach a filled valence shell. The table below shows the number of bonds these elements typically make to achieve an octet. So here, beryllium is only going to make 2 bonds. Notice it does not have any lone pairs. It's actually going to be a violation of the octet rule because it only makes 2 bonds and has 4 electrons maximum. Boron is only going to make 3 bonds. It's another violation of the octet rule because it's only ever going to have 6 electrons maximum in its structure. The carbon family, so carbon and silicon, are going to tend to make 4 bonds. This could be 4 single bonds. It could also be 2 double bonds. It could also be a triple and a single bond. And you could also see it as a double and 2 singles. So there are different variations, but the idea is that there are a total of 4 bonds around the carbon or the silicon. The nitrogen family, so nitrogen and phosphorus, will tend to make 3 bonds and have 1 lone pair. So you may see this as a double, single, and a lone pair, or you might see it as a triple and a lone pair. Again, the idea is as long as you have 3 bonds and 1 pair, then that would be the typical structure for nitrogen and phosphorus. The oxygen family is going to make 2 bonds and have 2 lone pairs, and you could also write it as a double bond with 2 lone pairs. Finally, the halogens are going to have 1 bond, 3 lone pairs, and that's the only way the halogens could be written. Lastly, the hydrogen is going to be hydrogen and have only 1 bond, no lone pairs. These are the typical bonding patterns to have a formal charge of 0. So here is the ammonia molecule. Nitrogen has 5 valence and needs 3 more electrons to make an octet. By making 3 covalent bonds, the nitrogen is able to achieve an octet by sharing 3 electrons with the hydrogen atoms. Looking at the electrons arranged around nitrogen, notice that 5 came from the 5 valence electrons initially on nitrogen and 3 from the hydrogens. Since no electrons were actually transferred completely to nitrogen, its formal charge is 0. And so here you could also say that there are 5 valence for nitrogen minus 1, 2, 3, 4, 5, which is equal to a formal charge of 0. Or you could just recognize that this is a normal bonding pattern for nitrogen. 3 bonds and 1 lone pair. Automatically that means it has a formal charge of 0. These are the normal bonding patterns of hydrogens, so that gives them formal charges of 0 as well. Now look at this Lewis structure here. Note that these are not common bonding patterns for either the carbon or the oxygen. According to the periodic table above, oxygen typically makes 2 bonds to achieve an octet. But in carbon monoxide, the oxygen atom makes 3 bonds. How is this possible? We could imagine that the oxygen transfers 1 electron to carbon, and this makes the oxygen have a +1 charge, and the carbon have a -1 charge. But now the C negative and the O plus are both isoelectronic with nitrogen. The C and the O atoms can now each make 3 bonds to achieve an octet. The formal charge is -1 on the carbon and +1 on the oxygen. Notice that the carbon atom in the CO Lewis structure has an octet of 8 electrons, 2, 4, 6, 8. The triple bond contains 2 electrons from each bond for a total of 6 electrons that are being shared between the carbon and oxygen atoms. But if we ask how the 8 electrons on carbon determine the charge on the carbon atom, it must be concluded that only the 2 non-bonding electrons and 1 electron from each bond count as being on the carbon atom. This is a sum of 5 electrons. Since an isolated carbon atom has only 4 valence, it must be concluded that the formal charge is 4 minus 5, which equals a -1. The figure above shows that the oxygen atom contributes 5 electrons to the 8 electrons arranged around the oxygen. Since an isolated oxygen has 6 valence electrons, but it's only using 5 in its electron arrangement in the CO, it must be concluded that the formal charge on oxygen is 6 minus 5, which is a +1. Here's your note card for this section. Calculating formal charge, you take the number of valence of the element minus each dot minus 1 for each dash. Formal charges must equal the overall charge of the molecule. If you have to have negative charges as formal charges, then it should be on more electronegative elements. As many 0 formal charges as possible is more ideal.